Hi all, in this video we'll talk about minimum spanning tree, and the agenda of this video is first we will discuss what is meant by a spanning tree and what are the various properties of it. So later we will talk about minimum spanning tree. So to start off, first we'll discuss the definition of the spanning tree. So if you see the definition of a spanning tree, it is a subset of graph such that all vertices are connected using minimal number of edges. So let us understand this definition with the help of an example. So let's take this graph. This is an undirected connected graph. Now you have how many vertices are there in this graph? You have 5 vertices. Okay. So A, B, C, D, E are the 5 vertices. Like these are the 5 vertices of the graph. And if you see the edges, there are so many edges. Like if you want to reach E from A, either there is a direct edge that is going from A to E, or you can go to B. Like from A you can go to B, and from B you can reach E. Or there is another way. From B you can go to D, from D you can reach E, or from D you can go to C, from C you can reach to E. So to reach E from A, there are so many ways. Okay, but you will tell a graph as a spanning tree only if there is a single path. So basically spanning tree is like, let's say you have vertices, like let us take 5 vertices. You have 5 vertices here, right? So I'll draw another 5 vertices. Now you keep minimum edges. You should traverse all vertices. Okay, it's not that you remove all edges and make a graph disconnected. You have to traverse all the edges, but there should be minimum number of edges. Now here if you see from A to E, there are so many ways you can traverse. Like to reach E from A, there are so many ways, but that is not there are so many redundant ways also. So in a spanning tree you don't find that. So like if you this is one of the spanning tree. Now here if you want to go from A to E, from A if you want to reach E, you have to go to B, and from B you have to go to D, and from D you have to go to A. This is the only way present. And if you want to reach the C, from E you have to go to C. So if you want to go to B from A, there is only a single way, A to B. And if you want to reach D from A, there is a single way. You have to first go to B, and then you have to go to D. So this way what we have achieved is you can reach any vertex from any vertex. So what I mean here is, like from A I have reached B, I have reached D, I have reached E, and I have reached C. Likewise, that is applicable for all other vertices as well. So from B you can go to A. From B you can go to D. From B you can go to E as well. From B you can go to D. From D you can go to E. And from B if you want to go to C, you have to go to D. From D you go to E. From E you go to C. So from every vertex in the graph you can reach all other vertices. But there are a minimal number of edges. You don't have any redundant edge. So if you define it in a definition terms, so what you can say is there exists only a path, only a single path from one vertex to the other vertex. So from A if you want to go to E, there exists only a single path. From B if you want to go to E, there exists only a single path. You don't have multiple ways. So this way what we have achieved is you can traverse all vertices in the graph from each and every vertex, but you have minimum number of edges. Okay, you don't have any redundant edges. So that is called a spanning tree. So this is the virginal graph what we have seen here, and these are all the spanning trees. So like if you see, this is a subset of this graph, right? Because you just removed redundant edges. You just removed the so many edges, but still you made the graph connected. Okay, so this is called a spanning tree, where you can reach every vertex but with a minimal number of vertices, the edges. So this is one of the spanning tree, and you can't say that there exists only a single spanning tree for a graph. There exist multiple spanning trees. Now, if you see, this is one of the spanning trees, because you can reach you can reach all vertices, but like this is the combination I have selected. Now I can like create a subset of this main graph like this as well. Okay. So this way also you can reach, like from A, if you see, you can reach all other vertices. So this is one of the spanning trees and this is one of the spanning trees. So this way you can have multiple number of spanning trees for a single graph. Okay. Now, let us see the other properties. Now, this is also like this. Let us consider this is a virginal graph. Okay. So, first one is the virginal graph, and these are all the like spanning trees. So, if you see here, I have removed this edge in this graph. In this one, I have removed this. To form this spanning tree, I have removed this one, and to form this spanning tree, I have removed this one. So, like I have, like even if I remove the edges from A, I can go to C. Like I can go here from to B, from B I can go. So your graph is connected, but you removed few edges. So this way you can form a spanning tree. And the properties, if you see, in a spanning tree, let's say you have vertices 3, and like here you have 3 vertices. So spanning tree will have n minus 1 edges. Okay. Now that is one of the properties of the spanning tree. Now here you have 3 vertices A, B, C. So these are all the spanning trees, right? This is one spanning tree, this is one spanning tree, and this is third spanning tree. So how many trees you have formed? 3 trees. And how many edges you have in each spanning tree? Only 2. 2, 2, 2. So here n equal to 3. N minus 1 becomes 2. Here I have written. N is the number of vertices and E is the number of edges, right? So n minus 1. So in a spanning tree, you will have vertices, number of vertices in a graph minus 1. So here, like initially, I did not have these spanning trees in my mind. Now, as soon as I look at this graph, I see there are 3 vertices and 3 edges. So, how my spanning tree would look? So, in my spanning tree, I would have 3 vertices, because you don't remove vertices. You just remove the redundant edges. So, as soon as I look at this graph, I remember the properties of the spanning tree, and I say, okay, in my spanning tree, I'll have ABC vertices, but I'll have only 2 edges. Those 2 edges depends on my selection. Okay. So this is the property. So n equal to 3 and you'll have 2 edges. So those 2 edges you should select. You should select in such a way that the graph is not broken, and the graph is not broken. You can reach any vertex from any vertex in the graph. So that way I should select it. So what I have done, okay, my spanning tree should have 2 edges. So initially what I do, I'll remove this. So when I remove this, I'll get this spanning tree. And when second time what I do is I remove this, then I got this spanning tree. Third time what I have done, I have removed this one, BCH. So I have got this. So this way you can form a spanning tree. So this is the simple example where you have just 3 vertices and the 3 edges. So that's why just by looking you can form it. But there are complex graphs where you have multiple number of vertices and multiple number of edges. So there are few algorithms to form a spanning tree that we'll discuss in the coming videos. Okay, this is one of the property. And coming to the other properties, let's take a complete graph. So what is mean by a complete graph? So from each edge, so let's say A is the, from each vertex, like let's consider A is a vertex. So from A, if I have direct edges to all other vertices, okay, from A, if you see, I have a direct edge to B, I have direct edge to C, I have direct edge to D, and I have direct edge to E. So if I consider B, I have direct edge to A, D, I have direct edge, to C, I have direct edge, and E, I have direct edge. So likewise, it is the same. So from each and every vertex in a graph, you will have direct edges to all other vertices. So that is called a complete graph, Okay. So in a complete graph, let us consider a complete graph. To form a spanning tree from a complete graph, or a number of spanning trees that can be formed by a complete graph is n, like n power n minus 2. So let us see the formula here. If you see for a complete graph, number of spanning trees in a complete graph is n power n minus 2. So let us do that. Here if you see n equal to 3, okay, n power n minus 2, 3 power n minus 2. n minus 2 is n is 3 minus 2, okay. So 3 power 1. So 3 power 1 is nothing but 3, right? So n power n minus 2. So here you have got 3 graphs. So here it's a complete graph because from A you have direct edge to B to C. From B you have direct edge to A and direct edge to C. From C you have direct edge to A and from C you have direct edge to B. So this way, this is a complete graph, and the number of spanning trees that can be formed from a complete graph is n power n minus 2, which is 3. And also in a complete graph, by removing e minus n plus 1 edges, you can form a spanning tree. So what does that mean? Here if you see, this is a complete graph. How many edges it has? 1, 2, 3, 4, 5. And these are all outer edges what I was talking about. And here 1, 2, 3, 4, 5. So total edges, if you count here, you will get 10 edges. So E equal to 10. And how many vertices I have? 1, 2, 3, 4, 5. So 10 minus 5 plus 1, 6. So this is my graph, right? So this is a complete graph I can form. So in this, if you apply n power n minus 2 formula here, what is the n value here? N is the number of vertices. So n value is 5. 5 minus 2 is 3. So 5 power 3 spanning trees you can form from this. These are just sample spanning graphs I have drawn. So like I have used tree here instead of spanning graph. It was just interchanged. So 5 power 3. So 5 power 3 number of spanning graphs we can form here, okay. And it is formed by removing 6 edges. So if you see here, here you have 10 edges, right? And in the spanning tree, how many edges you have? 1, 2, 3, 4. So total, initially you have 10 edges and you have removed, you have 4 edges now. So how many you have removed? 6 edges you have removed. So by removing E minus N plus 1 edges, you can form a spanning tree from a complete graph. This is only for a complete graph. Whatever formulas I have spoken here, like n power n minus 2, number of spanning trees, and by removing E minus n power n edges, this is applicable only for a complete graph. For a non-complete graph, these formulas are not applicable. Okay. And number of edges, as we already spoke, number of edges in the spanning tree would be vertices minus 1. Okay. So this is about spanning tree. Now let's come to the minimum spanning tree. What is mean by a minimum spanning tree? So minimum spanning tree is applicable for a weighted graphs. So spanning trees is applicable only for like undirected connected graphs, because the main intention here is if there are so many real world applications of this spanning tree. Okay, now let us consider you have a telephone network from, like, let's consider India. Okay, in India there is a main station at Delhi, and you have to send telephones, like telephone waves, circuit to different cities like Mumbai, Noida, or Kolkata and Bangalore. Okay, now to send it, uh, like you have to have a minimal number of lines or electric lines where you can send your telephone, like your telephone waves to all cities. So in such kind of example, what you will think is, okay, I should form a circuit from my main station from Delhi to these different cities. I should form a station with minimum number of electric lines, okay, or with minimum number of cables. So in such if you have such kind of like need, then your spanning tree, you can use spanning tree in such kind of examples. Or not even that, even if you take an electric circuit, there is a main power station from which electricity gets distributed to multiple cities. Okay, in those cases as well, like you should have, minimum number of cables. Like you can put large cable, like you should, if you want to have a minimum number of cables, then you can use this spanning tree in real world examples. Now first we'll talk about this minimum spanning tree. So minimum spanning tree, it is applicable for a weighted graphs. So spanning tree we already spoke for undirected connected graphs. So in minimum spanning tree, you have to add one more condition: weighted undirected connected graphs. Okay. Now this is the graph in which you have edges, like weights on your edges. Okay. Now how, like, I have to create a spanning tree out of this. So here, how many edges you have? Like three edges, and this is a complete graph, right? So this is one of the spanning tree, and this is one of the spanning tree, and this is one of the spanning tree. So you start calculating edge of each spanning tree. Here, if you see, you have removed this edge, right? So 10 and you have 2. 12 is the weight of this graph. And here, if you see, 5 and 2, 7 is the weight of this graph. Here you have 10 and 15. 15 is the weight of this graph. So as like I was telling you, real world examples like telephone circuit or the electric circuit, right? So in the electric circuit or telephone circuit, if you want to, send electricity to all stations with minimum cost, maybe like if you want, if a cable from A to B takes 10 rupees cost, and if a cable from A to C takes 2 rupees cost, so here from here electricity should reach from A to B and C. So if I use this connection, if I create a cable from A to B and A to C, my weight would be, or my cost would be 12. And if I create a connection from A to C, and from A to B, I don't select. From C to B, I create one more connection. Then my weight would be 7. So here it would be 15. So if I'm forming a network, electric circuit network, so if I choose this, I will end up paying minimum cost. So these way, like a minimum spanning tree is like, it is a weighted connected undirected graph in which your graph will have the minimum cost. Cost here is the weights on the edges. Okay. So this is my minimum spanning tree for this graph. So my minimum spanning tree is 7, this graph. So these are all my spanning trees, but this spanning tree is having the minimum weight on its edges. That's why you have, you say that this is a minimum spanning tree. So there are so many algorithms to find out a minimum spanning tree. Like you have Prim's algorithm and Kruskal's algorithm. We will discuss about those algorithms in the coming videos. And as I was explaining, this is mainly used for the real world applications like the electric circuit network or the telephonic network. Yeah, thank you.